Right. Okay. So yeah. So this is a topic out of like a course that we do for professional programmers, and it's aimed at people who already know Haskell to some degree. And so this is kind of one of the advanced topics, but I think it's a rather important core topic that I think everybody should know. And as I was saying a moment ago before the recording started, I think it's something that doesn't tend to get taught very well. So some of this many of you will already know, but hopefully it'll be useful for some people. And the purpose is to try and start to build up a mental model of how does evaluation work, what is really going on, and therefore how expensive are the things that you are doing, so that you can make predictions about performance of things, particularly how much memory is being used when you evaluate things. So yeah, we'll start off with evaluation. So yeah, this is about what gets evaluated and when. When people normally teach functional programming in Haskell, they teach about what are you evaluating, what is the answer, and people say, well, it doesn't really matter how it gets the answer, it just does. But this is all about how do you get the answer, what steps, what is the order in which things happen, and what stays in memory while it's going on. So this is important just for performance, for space use, but it's also, if you ever want to do things in parallel evaluation, you have to understand evaluation before you can understand parallel evaluation. So we'll start off by looking at how does evaluation work, how does Haskell's choice of evaluation order work, and then how can we change that? Like what's the default, and then how can we influence that to change the order in which things evaluate if you know that you need to change the order. Okay, so we'll start off by looking at reduction. We're looking at pure terms, right? We're talking about the pure evaluation of Haskell expressions, not like imperative or monadic stuff. Anything that's part of the pure part of the language. So we're back to simple stuff here, okay? So in a term, a Haskell expression, a sub-expression that can be reduced is called a redex. Let's look at, and redex is normally, this is the typical form of evaluation, and usually it's when you are evaluating or reducing a function call. You're replacing the left-hand side of a definition with the right-hand side, as in the mathematical style of Haskell's function definitions. And it's equivalent to beta reduction or to beta reduction from lambda calculus. So then an obvious question is, well, what if there are multiple redexes in one term? And we'll look in a second about examples of where you get redexes. Because you can have expressions where not everything in an expression is reducible. There are parts of an expression that are reducible immediately, and other parts that are not reducible yet. But what if there are multiple redexes in one term? You have a choice. Does it make any difference? So let's start by looking at an example. How many redexes are there in this term? So remember, the redex was a part of a sub-expression that can be reduced, that can be evaluated. And by evaluating, remember, we meant replacing left-hand sides of a definition by the right-hand side. So using the function definition to do one step of the evaluation. So point out, where are the redexes in this term? What can be evaluated at this stage? Okay, so each occurrence of ID here is applied to an argument, and so yeah, we could replace the left-hand side by the right-hand side in the definition of ID. And is that everything? I think it is. Yeah. So yeah, each of those are sub-expressions of the original expression. Of course, the top level was an example as well. And so each of those applications of ID were places that could be reduced. What about this one? Sub-expressions that can be reduced. Three. So each of the pluses can be reduced immediately, or the application of the lambda expression to the two arguments could be. Well, actually, maybe strictly speaking, we should say that it's really application of the lambda function to the first argument. Yeah. So that's why it's to the first argument, not to both of them. Yeah. Okay. So those are multiple. There are choices about which bits of an expression can be reduced in principle. So then the next question is, what does the order matter? So let's look at the possible reductions for this example. So again, we're not yet going. A lot of you already know that Haskell makes a particular choice, but we're just starting from looking at this from a sort of simple mathematical point of view of just expressions and definitions. What could be reduced? Well, you've got two functions applied to arguments. You could reduce head, right? Or you could reduce repeat. So okay, let me do this one on the board then. Do I have a thing I can use for this? Sure. So okay, I'm just going to use head and R for repeat. So head and repeat one. So we've got the choice of reducing. Okay, we can't actually reduce head yet, can we? Because what was the definition of head? Head of cons, x cons x's was x. So actually, we can't reduce this yet because this does not match the pattern for the definition. So in fact, initially, the only one that we can do is the repeat. So the repeat says repeat of x equals x cons r of x, right? That's the definition for repeat. So this can be reduced to squiggle head of 1 cons r1. Now we've got a choice, right? Because now we can reduce either this one or this one. So okay, in one choice, if we reduce r, if we pick that as our choice, then of course we're going to get 1 cons r1. And that line of evaluation is going to go on forever, of course. Or alternatively, we could choose to reduce the head at this point, and then say, well, that reduces immediately to 1, if we using the definition here. So, okay, I mean, this is a noddy example, simple example, but what does this tell us? It tells us, first of all, there's choices, and second of all, the choices matter. In this case, the choice matters between terminating and not terminating. So, okay, evaluation order, or this isn't so much order, but the choice of regex matters. All right, let's look at the next one. So this one says minimum is we're defining minimum as the head of sort of x's. I'm not going to define sort, but we can. So let's look at this example. Because this shows a slightly different outcome. So starting with head of sort of, what have we got? 4, 1, 3. All right, so we can't reduce head because it doesn't match the pattern yet. So we have to reduce sort. I'm not going to take the sort definition, but let's assume that this reduces to head of 1 cons sort of something or other. Doesn't really matter, but because I'm making assumptions about how sort works, but it doesn't really matter at this stage. Okay, so now we've got the same kind of setup again. We've got a choice. We can either reduce head now, or we can reduce sort. And okay, this time, if we do this, if we keep going down the line of reducing sort, of course we're going to get 1, 3, and if we, a number of steps, ... eventually we're going to get to head of 1 cons 3 cons 4 cons empty list. And that, of course, now we've got no more choices about reduction order. Now, of course, we can only reduce to head of that list. We can reduce head, so that, of course that reduces to 1 again. So if we had chosen differently at this stage, if we had chosen to reduce head here, then of course we'd have got 1. So what does this example illustrate? Both of these choices terminated. They both terminated with the same answer, which is good. But they terminated in quite a different number of steps, right? One terminated quickly, one terminated a lot slower. So the first example shows us that evaluation order matters for termination, and this example shows that it matters for performance. So evaluation, choice of evaluation strategy, choice of redexes does matter, not for the answer. Well, it matters for the answer about terminating or non-terminating, finding an answer, but it matters for the performance of finding the answer. So, I mean, as you know, Haskell uses lazy evaluation. What does that really mean? I mean, intuitively, their expressions are evaluated when they're required. That's the intuition behind the word lazy. Do it when you need to. And the rule is, when you have this choice between redexes, the rule that Haskell, or that lazy evaluation chooses, is the leftmost outermost. And we'll look at what does that mean exactly. Okay, yeah. And then, so leftmost outermost gives, if you only choose leftmost outermost as your strategy, that gives you what they call by name evaluation. And then lazy evaluation adds one additional feature, which is sharing of redexes, sharing of things. So in particular, the rule is whenever an identifier is bound to an expression using like a lambda argument, a let, or a where, anywhere where you bind a name to a value, this equals that, let and where, but also function arguments or lambda arguments. Those are binding, and then applying that function to something, that is binding a name to an expression. And those names then only get evaluated once. And that's an important part of lazy evaluation. We'll get to that detail. But let's just look at leftmost outermost first. So and let's look at it in this example here. So by outermost we mean that we would, if both of these are choices, we would choose the outermost one, the one that is furthest to the outside, or if you look at it as a tree, furthest to the top. So this would be the outermost one, but of course this one's not a redex here because we can't actually apply it yet. So this one's not a redex in this case, but if it were, that would be the outermost one. And where there are multiples, so supposing you've got f of x or something concrete, f of 3 plus f of 4, if you have that as your expression, what's the outermost, well, the outermost function application, of course, is this binary operator, but this is not a redex yet because plus needs both of its arguments to be in normal form first. But so here's an example where you've got two redexes on the same level, and the answer is you pick the leftmost one. So that's essentially an arbitrary choice, leftmost rather than. The important one is outermost, that we reduce the outermost redex first. So in this case, that says, well, of course, here the outermost redex is S because it's the only redex. But once we get to this stage, we now have two choices. We can H is the top level application of the function to the argument is a redex now because the arguments are the right form. It matches the definition. And the sort function was also still a redex. So here we had a choice, and H was the outermost one. Head here was the outermost redex. So normal order. So sorry, not call by name and lazy evaluation would both say that this is the one that you pick at this stage, and so that one's the one that reduces. That's the efficient one, right? That's the one that reduces to 1 immediately, rather than. Whereas call by value. Or the typical evaluation strategy that every other language uses would of course pick this one rather than this one. So it would follow this strategy. So call by name or call by name with memoization, which is what lazy evaluation is, picks this one, and call by value, which is what every other language does, picks that one. So okay, so that's what the leftmost outermost rule is. Does that make sense? Okay. And then there's another important bit of terminology, which is normal form. When there are no more redexes available anywhere, then you've got to normal form. So, I mean, obviously these cases are normal form. There's another very important bit of terminology when it comes to talking about lazy evaluation, which is weak head normal form, which we will very often abbreviate to WHNF, which is completely unpronounceable. WHNF. So in lots of the questions that are coming up that we'll do, the question is, is this which things are in weak head normal form? So what is weak head normal form? We said that normal form is when there are no redexes left whatsoever. But weak head normal form is when the top level of the expression is either a constructor or a lambda. So what does that mean? So do we have examples here? I can't remember. I haven't done this for a while. No, let's just do a couple of examples of what that means. So if I've got, where's the thing gone? Oh, it's right there in front of me. So top level of the expression. So remember, top level means, yeah, I mean, that's fairly obvious. You know what that is. This is the top level. This application of this function to this argument is the top level thing there. So if you've got a constructor as the top level, like just of 1 plus 1, right? There's still a redex here, which is that, but this is in weak head normal form because the top level is a constructor. Another example would be right? This is again still a redex, but because the top level expression is a lambda, this is also considered to be in weak head normal form.
Even if instead of 1 there was a function call?
If we change this to anything else, it doesn't matter, yeah, because the point is the top level expression here is the lambda. So because it's a lambda, it is in weak head normal form. So yeah, obviously anything that has no redexes left is necessarily in weak head normal form. But anything that has a constructor or a lambda as the top level is weak head normal form. And we'll see that come up many times. So remember that definition. It's because that is how far Haskell evaluates. I mean, we'll see this. We'll see more of this. But the reason that weak head normal form is important is because when we say that Haskell evaluates something, like when you do a case analysis, you're evaluating it to weak head normal form, because that's the minimal amount of evaluation that's necessary to make progress, to reveal what the structure of something is. Like right here, to be able to check if this pattern matches, we had to evaluate the argument, the sort here, to reveal a constructor, the constructor being the list cons constructor. So we'll see more examples of that. Okay. I mentioned that already. Call by value or strict or eager evaluation that you get in lots of other languages corresponds to choosing this strategy. Arguments are reduced as far as possible before reducing the function application, usually left to right. So yeah, you evaluate the argument before evaluating the function, before evaluating the application. Call by name. As I was saying a second ago, the call by name would also pick this route. The difference is the memorization, whether something that's bound to a name is evaluated once or multiple times. And if you've ever used some of the crazy scripting languages like M4 or makefiles, you may have come across this fact that a thing that's bound to a name gets expanded every time it's used, not just like the first time it's used. And that makes a big difference to the performance. So yeah, Haskell uses call by name, but it adds the sharing, so that if something is named and shared, it's evaluated at most once. Yeah, so in this example here, the x value, or the x variable rather, is used twice here in f of x and g of x. But if we apply this function to something, so some term will get bound to x, that term will be reduced at most once. I mean, it may be reduced 0 times because it may be that f and g never use it. But supposing that both f and g do end up using x, it'll only get evaluated once, even though it gets used twice. So that's the important difference with lazy evaluation. It gets shared. We'll talk a bit later about how that works. If you were ever studying this kind of stuff, like university course or a book, you might have come across this that says that if you can reduce a term in 2 different ways, you eventually basically get to the same answer. They can both be reduced to a common thing, which is equal. So in this example, we can reduce both of them to a normal form, which is equal, but in general, they can be reduced to something in between that's equal. And so that tells you that if your language obeys the Church-Rosso theorem, then it means that the order of evaluation doesn't matter for the result. Like what answer you get, you're not going to get 2 in one case and 1 in the other case. But yeah, it doesn't tell you about non-termination or efficiency. And so then a consequence of that is that there's exactly one normal form, which is the intuition which that everyone gets taught when they're first learning functional languages, which is that the order of evaluation doesn't matter for the purpose of what the answer is, but it does matter for the performance. And here's the really nice thing. Why does Haskell choose lazy evaluation? It's because if a normal form exists, right, because not every term necessarily has a normal form, you can obviously write down non-terminating terms, but if a normal form does exist, lazy evaluation will arrive at that normal form. So that's a nice property. And that's why lazy languages do that. I mean, it's because of that fundamental theorem about evaluation. If there's an answer, lazy evaluation finds it, whereas eager evaluation is not guaranteed to find it, as we saw with the example with repeat.
Repeat doesn't have a normal form.
No, but head of repeat does, which was the example that we were doing. Yeah. So you're right. Repeat does not have a normal form, but yeah.
So it might arrive in the answer just in the time.
That's kind of the same thing as saying it won't do it. Yeah. Yeah. I mean that is a non-terminating example under strict evaluation. Let's see. Do I want to run through this example? This sort of thing you've probably seen dozens of times. I mean, this is just an example of why is it useful to have this style of evaluation. It lets you do things with supposedly infinite values because the lazy evaluation, or rather the call by name evaluation is what's really required here. Means that we only evaluate as far as is necessary to compute the answer. So we can evaluate this to normal form under a lazy evaluation model, and it will terminate. Whereas the same thing under a strict or eager evaluation model would not terminate. And so that means that we can write things like this. We can use this kind of style. Whereas you couldn't use that kind of style you can't use that style in ML, right? Or Scala or not directly. Well, you can use streams which are in encoding with lambdas, but it's not as straightforward as just like constructors, terms, and so you can simulate those things. You can simulate streams, but it requires more. And you don't get sharing for free. You've got to explicitly, the typical thing with streams, if you evaluate the stream the second time, you evaluate it a second time. This will do the sharing. And it does it as part of the usual way that the evaluation mechanism works. Okay. So what actually drives evaluation? This is important for building up your mental model of how does this work. Okay, if you're using GHCI, then obviously we can define these things, but what causes that to be actually reduced and printed? Well, it's actually the fact that GHCI wants to print the result. And to print the result, we need to have the expression in normal form, fully evaluated, otherwise we can't show it. And then it's the trying to actually it's trying to call show on the result that then causes evaluation of everything else. So if we were putting this in the GHCI prompt, it's the fact that it's trying to show this that's going to drive the evaluation. And similarly for a complete program, it's main that starts at the top and drives evaluation from there on. But that's kind of not really the most important point. The really important point is about pattern matching, case analysis. That's really what drives evaluation. So, in the example of trying to say print, like if GHCI is basically calling, print of head of sort or da 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 da. It's the fact that print, itself does case analysis, right? Print is trying to look through each character one by one to be able to print them out on the screen, and it's the pattern matching, the case analysis, that is actually what drives evaluation. So, in this example here, if we're trying to reduce this, what drives evaluation is that head needs to see this pattern. It needs to see whether, it needs to see in which case it's in. Let's get rid of that one and just look at the definition of head again. Head has these two cases, and that's obviously error. So head is defined in two parts by case analysis, by pattern matching. And to determine whether we're in this case or this case, we need to have evaluated the argument at least to weak head normal form, in fact. Weak head normal form tells us the top level constructor. The top level constructor being either the empty list or comms. So it's really, what drives evaluation is pattern matching. Whereas, if we had an identity function, we can apply that and reduce that without doing any further evaluation, really. Or we can pass, or these arguments here, these ones do not get immediately evaluated by doing this reduction because they're not pattern matched on. So it's pattern matching that drives evaluation. Yes. So the crucial idea really is that it's the patterns that tell you how far things have to have been evaluated to be able to make the case distinctions. If we had a different function, that wasn't head, it was something else entirely, but it did it by pattern matching on lists, some kind of function. And supposing we had one that did something special for 3 and something different for the general case of whatever it is. So this forces this, to be able to make a distinction between these two cases for evaluation to move forward, for us to decide, which definition do we reduce, which definition do we use as part of the reduction. We have to have not just evaluated in this case, the top level constructor. We have also had to evaluate, the X to see the first, the head of the list, to see is it a 3 or not. So again, it's pattern matching. This is obviously, a constant pattern. So it's pattern matching, and the shape of that pattern is crucially that tells you what has to be evaluated to be able to make the case distinctions and move to the next reduction. Does that make sense?
Yeah, but how do we know to evaluate more than just weak head number form? Because the first pattern needs to evaluate the
to make the distinction. So okay, so these are compound patterns. So if we were to split that up into a series of simple patterns using just case analysis, using just case expressions, we could redefine this as f of A equals case A of, and we're only going to use simple patterns now, not compound patterns. So we'll just say B cons B's or empty. And in this case, we're going to do, sorry, I'll need more space actually. Case B of 3 or anything else. So to distinguish, so
that's separate step, right?
and each of these case analysis, each of these case expressions does evaluation to weak head normal form. So we have to reduce A to weak head normal form to distinguish the different constructors, and then we have to, within this case, have to reduce that to weak head normal form, which of course for an integer is just normal form, to distinguish 3 from not 3. So yeah, case analysis does forces reduction to weak head normal form, the outermost constructor. We'll come to the lambdas later, they're more subtle. But for constructors, it's quite straightforward. And compound patterns turn into nested cases, basically. And that's actually what the compiler does internally. Yes, exactly what we just said. So evaluating to wuhanuf reveals the outermost constructor and lets us make a choice on that constructor and then move on.
It should be called woof.
Woof.
Woof evaluation. Because of the pronunciation.
Yeah, maybe it should. Yeah, I like that. Maybe I'll call it that in future. Right. This is another part that when I was learning Haskell. This was something that this idea of understanding the demand as looking backwards through the function. It was something that I realized later was really useful for me for understanding what's going on, for understanding what is going to be evaluated. So being able to learn this technique for looking at a definition, looking at a function and saying, tracking demand backwards from the results back to what is it going to demand about its arguments. And it proved to me to be a very useful technique to be able to learn, to be able to, in your head, look at a function, not ones that are fantastically complicated, but ones of ordinary sort of complexity, and be able to do this backwards demand analysis in your head. So I will try and impart the idea of that, but to do it for real, you have to practice it. But I found it to be very useful, so that's why I'm highlighting it in front. So let's get into what does this mean and how do we do this. So this is the case where you are looking at the definition of a function. So in the examples we've been looking at so far, we've been looking at reducing expressions, but it's very often useful to look at a single definition on its own, a single function definition, or sub-expression of a term, and to find out and to ask the question, what demand does this place on its arguments or on its surroundings or its environment? So you look at one function, you say, someone else is going to call this function at some point. So I can assume that the results of my function are demanded, right? That's a starting assumption. Because if they weren't demanded, no one was ever going to call my function in the first place. So you can start off with the assumption that the results are demanded. And then you look at that and you say, okay, the result here's where it returns a result, or here's the top level in one of the cases, in one of the many cases, like down here, in this case down here, a result is being returned. What demand does returning that result place on the arguments to my function? Like, for example, here, or more generally, all the various variables that are within the arguments. So the question you're looking at is, given that the result is returned, and the result itself is always going to be in weak head normal form. That's the other key part, right? When a function gets called, it's called in the context of a case analysis somewhere else in the program, and it gets called to reduce to weak head normal form. So the function, when it is called, is going to have to return a result in weak head normal form. So the question you want to ask then is, given that this result somewhere here is going to be returned in weak head normal form, what does that do? What does that to evaluate that to weak head normal form? What else did I have to evaluate to weak head normal form? For example, did I have to evaluate, the arguments to the function, or something else that's defined elsewhere? So let's look at a couple examples. With the identity function, this is a trivial example, but it's actually slightly interesting. Demanding the result of this function, demanding the result of ID, will demand its argument. So let's just go through that. So we are thinking inside the context of the definition of ID. We're not thinking about the call sites. We're just thinking about its definition. And we're saying, someone else is calling me. Someone else is calling the identity function. I return x. And x had better be in weak head normal form, because when the function returns, that was, it was being called in the context of some case analysis. So the result had to be in weak head normal form. So I had better evaluate, x, the input argument, which of course is exactly what I'm returning. The argument itself, I will need to evaluate that to weak head normal form. So in some sense, ID does do evaluation under this way of thinking about it. I mean, you could say that ID does no evaluation if you just think about it as these kinds of reductions. But the way that, by taking this initial assumption that no one is going to call my function unless it's to look at the answer and to see that the result is in weak head normal form, we can say that actually, and that's the strategy that that Haskell really uses. So x is being returned, therefore it has to be in weak head normal form. What else had to be evaluated to get x into weak head normal form? Nothing. X had to be evaluated to weak head normal form. So we can say that the identity function does place demand on its argument. It will have to evaluate x to weak head normal form, which is the argument. Does that make sense? I mean, it's slightly odd, but do you see what I mean? All right. Let's do the same thing here. So this also returns a variable x, which is one of the arguments. So x has to be evaluated to weak head normal form, because that is the result that we are returning here. So it places the demand on the argument, which is of course just x, to be in weak head normal form, and that's it. So therefore we can say that there's no demand placed on y, because we never said anything about y. But we did say something about, we had to evaluate x. All right. What about this one? So there are two places where we return a result. Obviously the case where it says true, and the case where we are returning y. So how do we think about this one? So true is of course already in weak head normal form, but what did we have to do to get what did we have to demand to get to that stage of returning true? We had to distinguish which case we were in. And so what did we have to do for that? We had to so what case analysis had to happen? We had to do case analysis on the first argument. This is obviously a binary operator being defined infix, and it's being defined by pattern matching on its left-hand argument, its first argument. So to return the result true is already in weak head normal form, so there's no additional demand placed by that. But we had to do the case analysis, and so the case analysis required the first argument to be in weak head normal form. So, okay, so in that case, just the first argument had to be evaluated to weak head normal form. And in the second case, what's the analysis? Okay, we're returning y, therefore y had better be in weak head normal form. And additionally, of course, we had to still do the case analysis to, either way around, we had to do the case analysis. So the overall way to think about this one then is that we always evaluate the first argument to weak head normal form because we have to do the case analysis, to do the pattern matching. And in the case that the first argument was true, we also demand the second argument. But in the case that the first argument was, when the first argument was false, we demand the second argument. But when the first argument was true, we did not. So it's a conditional demand in that case. Very often the demands are unconditional, but in this case the demand is conditional. But you see, we're going backwards from the results back to what does that say about the arguments? Does that make sense? Okay. Someone walk me through this one.
Evaluate the second argument to
First, the case analysis.
to do case analysis,
Mhm.
and if
Right.
it's not empty, we have to also evaluate first.
Okay, let's do, yeah, so the first bit, as you said, was because we can see it's defined in parts and it's defined by pattern matching on its second argument, we must evaluate the second argument to weak head normal form.
We don't have to evaluate.
Right, okay, so yeah, the first case is really easy. Okay, so first bit, yeah, second argument has to be reduced to weak head normal form. In the case that the argument was empty, we're returning empty, and that is, of course, already in weak head normal form. It's a constructor. In the second case, what's happening in the second case?
Returning a constructor.
Yes, the result there is already in weak head normal form,
Yeah, so nothing really gets
so nothing else happens.
So we don't need to know F to
We don't need to know f, or x, or x's. Yeah, so that's the crucial point here, is that the cons here is the top level constructor, is the top level term, the top level of this expression. It's infix, which just makes it a little bit confusing. But the cons is the top level thing, and it's a constructor, and that meets the definition of being in weak head normal form. And so that's it. We stop there. We only need to return in weak head normal form. So no further evaluation is caused by map here. And that corresponds to what we expect of map, right? Map doesn't. You can map over, lists of undefined, or we don't expect map to force the evaluation of the elements. And if we only evaluate, some elements of the, or if we only walk down the spine of the list a few elements, like if we do take, like our example earlier, take 100, we're not evaluating map again. We're not evaluating the tail, and that's because, in both cases, the first and second argument of the cons are not required to be evaluated. It's only because the cons is already weak head normal form. Okay. So I think it's useful when you are going back and looking at code that you write to practice this technique of look at your definitions, and especially if this even works in more complicated situations where there's let clauses and where clauses, and say, well, in this particular case, obviously I had to do the things that were demanded for the case analysis, but I'm returning some result that depends on something which is defined in a where clause. Do I demand that or not? And by doing things like, by doing questions like this, is it inside an argument to a constructor that was defined in a where clause and therefore it won't be demanded, or is it something that I had to further evaluate? So you can do this. You can do this backwards demand analysis by looking at your definitions, including in the more complicated cases where you've got let clauses, where clauses. And I think that's a really useful technique for you to develop and practice, because it tells you it tells you what the strictness of your functions are. just by looking at them. But we can also do, there's also another technique for doing this, which is more of a, instead of like analyzing it in your head, it's a kind of more of an experimental technique. You just, science, let's just try it, let's just find out. So we don't actually have to look at the code in order to track demand. We can experiment. And the idea is that we set us up the bomb and then see if the bomb goes off. So the bomb is a non-terminating computation. So we feed the bomb into the function, and we demand that the result of the function be evaluated to weak head normal form, and we see, does the bomb go off? Right? The non-terminating expression being, something that throws an exception. That's our bomb. And the idea there is that if the function does produce a result, then it couldn't possibly have touched the bomb, because if it did touch the bomb will explode, and then we would see that the thing exploded rather than returning a result. Right? So there's only one slight quirk to this, is that, okay, so I said a bomb, but what I really mean, we feed in error or undefined, something that if evaluated would throw an exception and just stop evaluation, or terminate it abnormally. But if a function doesn't terminate, right, if it goes into an infinite loop, then we don't actually know whether it will eventually touch the thing and explode, or just never terminate. So we don't know whether it's going to demand the result in that case. So for this kind of corner case, what we do is we simply define that as saying it would have been okay if it did demand the result, if it did demand the argument, because that isn't going to change the answer, because we don't make a semantic difference between not terminating and terminating with an exception. I mean, that's a possibly controversial thing, but that just comes from the mathematics of all of this. The mathematics works out much better when we say that exceptions and non-termination are the same thing. They're both what in the notation we call them bottom. They're both non-results. So we can take this kind of experimental approach, but there's this corner case for non-termination. But for non-termination, we simply define that to be as if, or as good as, if it had demanded the argument. So this leads on to I said it's an experimental technique, but it's also an intuition for why does this mathematical definition work. So the definition of strictness is based on this idea of does it touch the booby-trapped argument. So a function, or a function of one argument, is called strict if, and only if you feed it in bottom, the result is also bottom. If you give it a non-terminating or an exception value, it returns either the exception value or itself does not terminate. Either of those two things are okay. But the easy way to think about it is you give it undefined and it returns undefined. It throws the exception that says undefined. Or indeed it throws any other exception, right? Because semantically we don't distinguish between different kinds of exceptions. So that's what motivates that mathematical definition. But that is then the definition for strictness, for a strict function. If you give it bottom, the result is bottom, either by non-termination or by crashing. Okay, so just note about that. In strict languages, all functions are strict because of the order of evaluation. That would always be the case, because the innermost, leftmost evaluation order will always touch all of the arguments. And so they would always have this property. In a non-strict language, like Haskell, there are still strict functions, but not all of them have to be strict. Some are strict in some arguments, but not all functions have to be strict in all arguments. Whereas in a strict language, all functions are always strict in all arguments. So yes, Haskell has strict and non-strict functions. Strict languages have only strict functions. All right, quiz time. And we can't have the same person every time. So just shout out what's the first one and why, and then we'll move on. What does this reduce to? Reduces to true. Okay. What about this one? Yeah, and that's because x goes to x, and so the bottom. What about this one? And why is that?
It doesn't force the argument, doesn't demand it.
Right. Yeah, so there's two ways of looking at that. One is the original way we did with reductions, but the other is by saying if we analyze the function there and do our backwards demand analysis, we can see that it does, as you just said, does not demand x because it returns a result in weak head normal form without placing any demand on x. And so when we evaluate it with bottom, the result is still the whatever it was going to be. Yep, okay. And this one, the next one. So yes, that one is indeed strict because it always returns bottom, irrespective, of course, of the argument that's given. And what about this one?
Returns lambda over one argument.
Returns f applied to bottom. Yeah, does everyone see that? Because this is a, this is a lambda with two arguments, but really that's the same as a lambda that returns another lambda. So if we're only applying it to a single argument, so we're applying it to the bottom is instantiated for the x, and that reduces to. Wait, what did you say?
It was wrong.
Yes, I was just thinking it through, and I realised the same. So what is the answer here?
It's a lambda of one argument.
That, which is what you said originally. I wasn't listening properly. Yeah. So the result is going to be lambda f applied to bottom, and that of course is in weak head normal form now, right? Because this is a lambda. So there's no further reduction because these were all. Yeah. Sorry, I didn't say at the beginning. These are all just reductions to weak head normal form, not reductions to normal form. And what does this next one reduce to? Reducing to weak head normal form. Reduces to 2. Yes, I think you're right. Why is that?
That doesn't apply the function.
Which is what we were discussing earlier. Yep. So that one's interesting. So what would we get as an intermediate thing? We would end up with.
What's the definition of map?
Definition of map was earlier. Where did it go? Yeah, let's run through that one actually because that's interesting. So I'll put the definition over here, and then we'll do the reduction on the other side. So map f empty equals empty list. Map f x cons x's equals f of x cons map f x's. So what was the example? It was length of map 2. Length map bottom of 1, 2. Okay, so what's going to drive evaluation first? So previously we were thinking about, at the beginning we were like read x's, but now we're thinking about it in terms of this evaluation strategy of outermost function using pattern matching to drive evaluation. So we've got a function applied to an argument. So we want to look at we need a definition of length as well. So length of empty. Let's use a simple definition. You can do a fold L or a fold R, but I'll do the fold R style. Length of So length requires its argument to be, well, it requires its argument to be in weak normal form to be able to distinguish the cases. So that's going to force the evaluation of this, right? And then to get map to be in weak normal, to get this expression to be in weak normal form, we have to evaluate map, of course. And it requires its second argument to be in weak normal form, which it is. So that will, we can already go down to here. So this will give us length. So that will be bottom of 1 cons map f of 2. Okay, so now, so this is now in weak normal form, so we can proceed with length, because that was all we needed. We only needed to get this to be the first argument for length, or the only argument to length, needs to be in weak normal form to be distinguished between these two cases. And that's what we got by doing that one reduction there. So we can reduce this on now to 1 plus, because we ignore x, we don't use it here, so length of map bottom 2. And then you can see obviously it's going to go on in the same pattern until we get to 1 plus 1. I'm running out of ink on this thing.
There's something more.
Until we get to 0, which will be length of map of the empty list.
Duncan, there is something more.
Oh, okay, okay. Length, we would eventually get down to there, which would then, of course, just then reduce to 2. So the interesting part of that was, cheers. And I hope these are whiteboard friendly. Permanent marker. Don't think I want that one. Whiteboard marker, there we go. That's dangerous, mixing the two in the same box. All right, just check. Yeah, there we go, okay. Yeah, so what was interesting there? Let's see. I mean, the main thing is, of course, is that we saw, here, that there's an intermediate point where you've got, bottom applied to 1, but because length never uses it, because it occurs here, we never demand x, and so therefore it all works out.
So in another way, we can look at this example that in length we are after an array of tanks, and in order to get to this form, we don't need really to care about bottom of something, yes, because we are after this first level of array of tanks, and
yes.
This stuff translates directly to this picture. I've got this
That's right.
Kind of picture of.
And we can see that from the definition of length, because it, I mean, all right, in this.
Here we omit this x, and when we omit this x, we can think about this as a tank. Yeah.
Yeah, exactly. Yes. So we never cared what x was. So it could have been bottom. It could have been a thunk. It could have been whatever.
It's called the spine of x.
That's right. That's right. And I was just going to say, because I mean, it looks like we don't evaluate x's either, but because it's recursive, we call length. Or eventually, we're going to call length here, and it's going to, of course, be distinguished again. So eventually, yes. We will distinguish all of the list constructors in the list, which is what gets us the spine of the list. But we never evaluate the arguments, the arguments to the cons, the first argument, the elements of the list. So yeah, so the x is. So yeah, we can see that is the pattern. That is the pattern by looking at the definition here, and the fact that it's recursive. Okay, so it is sometimes useful to do some of this stuff experimentally, and not just think about what the evaluation order is going to be, but to try it, test it. And so there's functions called trace and trace show from the debug.trace library. and they kind of cheat, but they let you observe evaluation order because they actually just emit things to standard error, I think. As soon as the first, they print their first argument when their second argument gets evaluated. We'll see another example of why does it have this slightly odd form of, returning its second argument. But the key point about trace and trace show is that they print out the first argument, and they just print it while evaluation is going on, right? So this is really there's a real side effect here, which is why it's only suitable for debugging, right? You should never. This is not a logging system, right?
Oh no.
I mean, internally there's unsafe magic going on here to print out stuff during evaluation, but it can be very handy. So here's this is a really tricky example actually. So we'll go through this. So supposing maybe I should just do an example in GHCI of what does this look like. Let's. Yeah, I was just going to say I will do that. Don't worry. This is not my first rodeo, as they say. Here we are, large text. Trace, wasn't it? So what was the type of trace? Or trace show. All right, so give me an example. Maybe we should do that one. Okay, I'm going to do a local definition of length. And len of sorry, that's what I wanted. And 1 plus. Does that look like the right definition? Okay. So if I do.
Actually, length of an empty list would be 0 on an empty list.
Yeah. Why did this type check? What is the type of this?
No milk survey.
Oh yeah, it requires the thing to be a num. Okay, that's why it doesn't make any sense. Okay. There we go. All right, so if we do now len of, what are we going to expect? Yeah. All right, so it obviously prints out the result at the end, and while it was evaluating it did the trace as a side effect, just printed stuff out to the screen. And does that make sense given the order in which these things happened? I guess it does, right? Because we're going down the list, cons, until finally we get to the tail of the list and print the. Yeah. Does that make sense?
Yeah.
Yeah. Okay.
And if you probably use sprint, then you should get this sprint, yes?
Sprint?
Yeah, I think it's for sprint.
Yeah.
You mean this thing?
Yeah.
Yeah, but that's.
You should get for this array of.
I can't remember how.
I think it takes an identifier. You need to say let x equals.
Ah, right. Yeah, this is a GHCI kind of debugging feature rather than a. Whereas the trace is really a function. It's just a function with a side effect. Yeah. Okay. So there. That was what you were meaning.
Yeah.
And now if I do.
But when you use length, then.
That was what you were after.
On x, yeah. Then you should get probably array with 5 times, yes, or something like that.
Well, no. Let's look at. This does make sense. When we first defined let x equals hello, x has not been evaluated at all. So sprint is showing it equals something. It's a func. That's their representation.
Already,
Yeah, not an array of
yes,
funcs. Whereas, yes, and then by the time we do, but sprint of is showing it as hello, not as.
Yes, because it's already evaluated. Yes.
Yeah, but why is it not showing it as a list of?
Probably pretty
Oh, because each of those are already in normal form. Let's do a different example.
I would use instead just a list of numbers instead of a string. I think it also works.
Oops, I'm spelling that wrong. Yeah, okay. Yeah, because the problem was that the list was already, each of those elements was already, the elements of the list were characters, and those were already in normal form. So sprint was showing us the whole thing rather than showing a list of, but if we do this one now, so len of course will still work, exactly the same as before, but if we do the sprint, it shows us that. Yeah, yeah. So sprint of course is a feature that's built into GHCI that shows. I mean, it's really looking inside the. It's not something that's definable in Haskell. You can't define sprint in Haskell. It's not observable. You can't see the funcs, but GHCI can, and so this is a special feature of the interpreter. You cannot write a function that does what sprint does. That would be violating the Church-Rosser theorem, and that's verboten. Well, that's also unobservable for the same reason. You can't observe time in pure evaluation. You can only observe that in I/O. And again, this is all stuff, Haskell bans all of those things because it demands that purity means purity and that the Church-Rosser theorem and all those sorts of things are true, because so that you get the mathematical properties that you expect. To get the mathematical properties you expect, you have to not allow evaluation to observe itself. So the question here was a similar exercise to what we just did, but it's slightly more complicated. So we're going to do, we've sort of annotated our special cons as being trace cons before returning x cons x's, and we've defined nil as being special version of the empty list, which does trace of dot before returning the empty list, and similarly for num. So these are all kind of wrappers, tracing wrappers around our constructors or number constants. Right, now we're going to define list to be the fold-R with our tracing cons and our tracing nil of map, the tracing wrapper around the real list of numbers 1 to 10. And then, so this list is the input list for our expression down here. So this list is going to use these tracing functions, these special tracing functions up here. But main is calling sum and take and drop, and those are the ordinary sum and take and drop, right? They're not special tracing versions. They get given a special list that, when evaluated, will print out its own evaluation. But these other ones don't do any other additional tracing, right? So everybody knows sufficiently well, hopefully, the definition of sum and take and drop, or at least can imagine what they are. I can write them on the board if it's helpful. Maybe I should write them all down explicitly. But start thinking about what is going to be printed, right? And of course, what is going to be printed requires you to know the answer of what is going to be evaluated in what order, because the trace is, when the trace happens, there's some bit of evaluation is going on. So. What are we going to see? In the meantime, I will write down some definitions. This is not as easy as it might look, but if you go through methodically, you'll get the answer. I will write down definitions of sum and take and drop. We probably don't need fold-R. I mean, remember that what fold-R is really doing is it's replacing all of the conses with the one argument and all of the nils with the other argument. In this case, of course, that's replacing the real cons is with our tracing cons, and the real nil with our tracing nil. So what we will end up building up here, I mean, if you want to write out what list, the equivalent thing, list would be equivalent to this, equals num1 special cons, tracing cons. Sorry, I'm writing this badly. Special tracing cons, num2 tracing cons, etc., 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 down to special tracing nil. Was it num10? So the list is just an ordinary list, but where we've replaced every element of the list and every constructor with a special tracing one. So really, this question comes down to, what is sum take 2 drop 3? When is it going to evaluate? In what order is it going to evaluate the constructors of this list? Which we will see because we've put special tracing versions of everything. So I'll just write down the definitions of sum and take and drop while you are thinking. And maybe I'll try a different, this is a bit dim. Oh, that's better. Sum. Take. What's the definition of take? Take 0 equals of x's. Drop. That's right. So, what do we think the answer is going to be?
5 columns and 0.
So you think it's going to be 5, so cons times 5, followed by 0. Oh, two nums. You mean?
Yeah, but num.
Oh, prints.
Print 0.
Yep. Yeah. Okay. So 0, 0. Okay. That's one proposal.
I think it's going to be 3 columns.
Three columns.
You think it's 3.
0, then another column.
Okay. Hold on. So one person thinks it'll be 3 followed by 0, 0, and you think it'll be
3 columns.
times 3 and
0, then a column, and then a 0.
does anyone want to? Who want? Okay, hands up for this one.
I want to change my
You want to change?
answer, but I'm not sure to what.
All
So, but it's wrong. But okay.
right. How many votes for this
I'm
one?
pretty sure it's going to be 3 columns.
Just because Martin said it doesn't mean it's right. I mean, he might be right. He might.
And I might miss a column.
First one.
So who thinks it's this one? 5. Okay. Who thinks it's this one? Nobody now. Who thinks it's the third one? Yeah, you're going to vote. You're going to vote for your own answer. Good, good, good. I have to actually type it in and find out. All right. No, I've got the. Let's see, which file is it in? It's in the exercises.
The sum is fold right, not fold left. This might be important.
No, sum is actually that.
Sum is that. Okay.
I think that is the definition of sum, actually. Sum probably should be a fold L, but I think it's
No, it's
defined.
fold
It's fold right in the prelude, but
Yeah.
it should be fold left. Not this one.
Let's see, where did I put the?
Compatibility with Miranda.
Where did I put the code for this? Oh, there it is. No, font's too big and I can't see it. No.
Can you just copy it as a block from the slide?
Yeah, I probably can. There we are. There we are. That's the one. Trace list. Okay. So what was the example main?
Can I have a first proposal?
Yes?
I think the answer might be dependent on the evaluation order of class, when in A plus B, whether A is evaluated before B or after.
Good question. What's the answer? Because you already know.
No, I don't know.
The left.
Remember?
I think,
Outermost, leftmost.
leftmost, okay.
So,
Okay.
yeah. This leftmost, rightmost doesn't come up very often, but that's an example where it would come up. Yeah, yeah. Let me just before I run it, let me just make sure we're going to be running the right thing. Otherwise, main might. No, okay, there we go. There we go. Okay, good. That's definitely going to print the one thing we want. All right, so the moment of truth. Okay, and it prints the result. Okay, okay, so actually it was 4. Oh, so yes, okay, so no, yes, okay, no one.
No, it's 5.
Is it? Am I just?
That's 3 zeros.
Yes, you're correct. Okay. 2 zeros. So this was the right answer.
The last zero is.
The last one is the 9, which was the result of.
There are 4 columns.
No, it's 5.
5.
2 drop 3.
2.
That's 3, 4, 5.
Okay.
Yeah. So let's try and understand that then. Why is that happening?
5, 10 more minutes.
Okay, sure. Yeah, that'll be. We'll do this and then stop. Or we can come back to strictness some other time. I mean, controlling evaluation order. I'll give you the slides so you can carry on the rest of it on your own. Why? Okay, so what's going on here? So dropping 3 elements from the list. So sum is going to do the first demanding. Sum requires its argument, and sum is going to look down the whole list it's given. So we should think about, because of this recursion and whatnot, okay, let's come back to whether the number will be evaluated before the cons. But the first question is, why is it 5 cons? It is not 3. So it's definitely going to have to evaluate all of the conses of its argument. We can see that from the definition. So how many is that going to be? Well, we know that sum is only going to get a take 2, but what did we have to evaluate? I mean, the result of take 2 is only going to be a list of length 2, but how much of the list did we have to evaluate to do that? Well, let's see where the demand goes. So take 2, take is going to demand its argument. It's going to force its argument, and to be in weak normal form, and that is going to force drop to produce results in weak normal form, which demands its argument. So what is drop 3? Okay, if before drop can return, it's going to be returning in this case, isn't it? Because that's going to be returning the remaining after dropping 3 elements. It's here is where it returns everything else. So to have done that, it has to have gone down the first 3 elements, doing pattern matching, and it's this pattern matching that is going to force the first 3 conses to be printed from list. Right? It's going to have to force those 3 just to get to this point where it returns a result to to take. Now, then we get to take 2. So before we've even reduced this, before we've even done the forcing implied by this pattern matching, we've now already printed 3 that was caused by drop. Now take is also going to, the result of take is demanded by sum. It produces conses, but not tracing conses. It forces its argument. It demands its argument rather. So, and we know that it's take 2, so it's going to do another 2, force 2 more conses, and so that gives us the next 2 conses, and then okay, so now so that gives us all 5 conses that we expect. Now, because remember, these ones are just ordinary conses, not special tracing conses. So sum itself is not going to do any pattern matching with cons that causes any further tracing, right? Because all of the tracing was forced by this pattern matching here or this pattern matching here. This for the first 3, this for the next 2. So none of them are caused by this. So what further forcing does sum do? It's only the evaluation of the plus, and that is what forces the arguments to be in weak normal form, which is finally what causes the num to be forced. And so then that's why we see the zeros after seeing the conses.
Yeah, basically, in one sentence, sum, when we look at the definition, really is into normal form. Yeah, because it needs normal form.
Yes,
so
yes.
If we think about it that way, then we can jump immediately into this take to drop 3 arguments, which really forces us to use 5 constructors.
Yep.
And then we've got to evaluate, because we've got the list of the length of 2. That's why these zeros, and that's say.
Yeah.
Since some pattern matches on the empty list, why there is no dot?
Because we never got to the end of this list.
Oh, right, because that's the only.
I mean, this one does this returns an empty, and it returns an empty when we get to take 0, which we got after doing take 1, take 2, take 2, take 1. But we never evaluated this one.
Yeah. Okay.
But
that's the special.
because this was not a tracing one. Yeah. Yeah. So we only looked at the first 5 elements of this list, and only looked at the first 2. We looked at 5, cons cells of list, and only 2 of the elements of it. Okay. Could I do, if I've got a few more minutes, let me do one other. I'm going to jump over this next topic about space leaks and go straight to controlling evaluation, because this is an important point, and you've probably seen some information about this, but I think it's useful to have it presented, all in one go. So we've looked at, there in principle are different evaluation orders, and Haskell chooses one default strategy, but Haskell also lets you adjust that strategy when that strategy is not what you would want. When you want to do that, when you want to do the order differently, then you want more control. So how do you get more control? You can only make things stricter. The data dependent, the normal evaluation order is already the least, it already demands things as minimally as possible. So the only thing you can do is to say, I want to demand it earlier or demand it anyway. Right? You can say, this will be evaluated later, but I'd like to evaluate it now because that's going to be cheaper. I'll not produce this thunk. I mean, I don't have enough time to go into what thunks are exactly, but many of you know what they are already. I don't want to delay the evaluation of this. I know it'll be needed later. I want to do it now. Or this may or may not be needed, but I want to evaluate it anyway. So in both cases, it's about doing stuff, evaluating stuff earlier or evaluating it more strictly. And why can that make sense? Usually it's to do with space and time. If you've got things that will be evaluated later, or it requires a little bit of memory and time for the runtime system and with the way the compiler sets things up, for the runtime system to keep track of things that will be evaluated later. And that keeping track of them can sometimes simply cost more than evaluating it in the first place. But in general, the compiler doesn't really know that. So it does that anyway. You as the programmer know that, but the compiler can't really know that generally. So you can know that it makes sense to evaluate this earlier. Sometimes there is actually strictness analysis that can work this out, but in the general case, it's you as the programmer who have to think about it and know that it makes sense. So how do you do it? So Haskell gives you the following primitive. And it turns out this has to be primitive. This cannot be defined within the language otherwise. And what this does is this says that it returns its second argument, which you can see it must do from the type. And it evaluates its first argument to weak head normal form. Or another way to put that is it's strict in its first argument. It demands both arguments because it returns the second one, but it also demands the first argument, even though it doesn't otherwise touch it. And that's why this has the same type as const, that returns its second argument and ignores its first argument. But while const is not strict, non-strict in its first argument, sec, or for sequence here, is strict in its first argument. And this is otherwise not definable in the language. So this is special. This is the primitive. And this is what Haskell gives you for controlling, for adding additional strictness, for evaluating things earlier than they would otherwise be. So you can use this to define other operators, and these are ones that you may have used before, and we'll see another example with bang patterns maybe if I have time. So this is the strict evaluation function. So this takes a function as its first argument, and it's an argument to that function as its second argument. And it uses the sec operator to say, let's evaluate x to weak head normal form, and then return f of x. And of course, returning f of x means reducing it to weak head normal form as well. So what's the effect of that? It means that we reduce x to weak head normal form, and we reduce f of x to weak head normal form. So basically, that means that we're making f strict. Even if f would not have demanded its argument, we are demanding it first. And in practice, what that really tends to mean is that x will be evaluated first. We'll evaluate x, and then we'll evaluate f of x. Strictly speaking, this doesn't require that it be done in that order, just that it be evaluated. But the typical behavior is going to be that x will be evaluated first, and then f will be called. So that's bringing up the evaluation of x earlier than it would otherwise be, right? Normally, x might or might not get evaluated inside of f sometime later. We're kind of hoisting that out early and saying, let's evaluate x now, and then call f.
I have a question.
Yes?
So what do you mean by saying that typically x will be evaluated first? Are there conditions under which x will be?
The definition saying that seek x is strict in x, seek of xy is strict in x, just requires that if you give it bottom, that if you give x being bottom, then the result is bottom. That doesn't actually tell you that it will evaluate x first and then evaluate f of x.
Okay.
It just says that it will be evaluated.
And what do you see that as?
GHC will take advantage of that looseness and typically do the most useful thing, which is why I was... I mean, the name is slightly misleading. I mean, seek is for sequence, meaning do this first and then do this second. But strictly speaking, it does not have to do them in an order.
Okay.
But the usual way of thinking about it is do this one first and then do that one. That's the easiest way to think about it.
There is PSEC that guarantees order.
Yes. Yeah, PSEC is subtly different from SEC in that GHC guarantees that it will do the evaluation of this one first and then do that one. And that's only important for parallelism, because then you really want to know the order in which things happen. Whereas for strictness, strictly speaking, the order still doesn't totally matter. It's the... Anyway, that's a much more subtle point than I wanted to get to. Okay, so you can have strict function application. Now, seek only evaluates to weak head normal form, like all other kinds of evaluation, like case analysis evaluates to weak head normal form. And by the way, you could not define seek in terms of case analysis either, because if you do case, if you were to do, right, if you do, I mean, I said that case does evaluation to weak head normal form, but only to do pattern matching. So if you do case, whatever of x, and then carry on, that still doesn't do any forcing. It's only to distinguish cases. So you still can't define seek within Haskell using case or anything else. It has to be primitive. So here's another quiz. Let's do this with seek. What is the first one? We're using strict function application for that one, because the strict application forces the argument before calling the function. So yes. What about the next one? Unit. Why is it unit and not bottom?
Comma is the constructor.
Right, because the tuple is a constructor, and so this term here is in weak head normal form because of the tuple constructor. That's right. Second, strictly applied to this tuple. One, for the same reason. So the strict application forces the argument to be in weak head normal form before applying the function, but this argument is in weak head normal form, again, because the pair constructor is a constructor. All right, what about the next one? So this evaluates this argument to weak head normal form, which it is, because it's a lambda. So basically there's no effect of the strict application here at all. So we just get that substituted for x, which then gives us the unit. What about this? So strict function application means that the argument has to be reduced to weak head normal form before calling length. To reduce this to weak head normal form, we have to call map bottom. The bottom won't be applied. So reducing this to weak head normal form would give us bottom applied to 1 cons map 2, map blah 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 2. And then we'd call length. So yeah, that won't do anything special. What about this next one? Seek requires its first argument to be in weak head normal form before returning the second. Because bottom plus 1, reduce that to weak head normal form is bottom. Doesn't have a weak head normal form. And the next one?
Unfortunately, plus is not a constructor.
Yes, plus is, yes, exactly. Right, because it's true. Let's assume that 1 is an int here. Yeah. So this one is unit because this term has cons as the top level thing. Yeah, and that is of course in weak head normal form. Very good. Maybe I should stop here. No, I'll explain this, and then because this is like one of the crucial things, and then I'll stop. I mean, I'm not going to go into. So earlier in the slides, the bit that we skipped over, we were looking at the problem with sum. Everybody knows that this is a bad definition of sum, but there's another definition of sum which also doesn't work, or doesn't do what you would hope, which would be, well, it's the prelude to this one. So this version of sum is going to be done in accumulator style. X equals go 0 of x's, and then go of, so here's our accumulator A, and when it's given the empty list, it's A, right? A for accumulator. Go A of x cons x's equals go of A plus x x's. Right, that would be the normal accumulator parameter style tail recursive version of sum using this tail recursive helper. And many of you will have seen this before, and you know that the problem with this is that although this is tail recursive, this still does not run in constant space because nothing demands A until the very end. So we build up all these thunks. Every time we call go again, we're constructing this, we're building this extra term, A plus x, and we're not evaluating it because the next iteration of go pattern matches on the the argument here, and it doesn't evaluate A because it doesn't demand it. We can see here it does not demand A. This can return, but only by the time it gets down to here, then finally we've built up all this big chain of funcs, and now because we do eventually return it, this is a result here. This has to be in weak head normal form because it was a result of go. Well, because it's a result of go. This doing our demand analysis, this is clearly demanded. It does demand that. But by the time it's got there, so it will eventually evaluate it all. You can't get away from some being, requiring everything to be in fully normal form. But we've built up this massive chain of funcs in the meantime in this accumulator. So this is an example where this result, these terms will be demanded eventually when you get down to the bottom of the list. But we would prefer to do it earlier rather than later. It'll be demanded anyway. Don't bother delaying it. Do it early. So what we would like is to evaluate this sum now. Before calling go recursively, we'd like to do it here and now, and not later when it's finally demanded at the result here. So the example using the things we've got so far, strict application, we could use strict application right here to say that this function applied to this argument, let's evaluate this argument strictly now before calling go again on the remaining arguments. So that would be the dollar bang strictness strict function application there, and that will solve this problem. And that means that now the accumulator is we don't build up this chain of funcs, and this will run in constant space because it's tail recursive and nothing else is building up any funcs, and then that's a good solution. That said, we would never recommend anyone write this particular thing in this style. The much nicer style, do I have it on the slides? Where is the bang pattern? I'll just do it here. The style that we would actually recommend uses a lot of you. Who's seen bang patterns before? Okay, most of you have. So, but let me just write this anyway. So where were we? Go A plus x x's. So as an alternative to using the seek operator or using things based on the seek operator, we can use bang patterns. Now actually bang patterns are also defined in terms of the seek operator, so ultimately it all comes down to the seek operator. But it's in almost all cases, it's a nicer way of adding strictness to use bang patterns than to use strict application or explicit uses of seek. And so a bang pattern, if you say f a, I can't remember if it needs to be, this kind of, it doesn't. I don't think it requires a parentheses. No, it doesn't. So a bang pattern is part of the pattern matching syntax of Haskell. There's also an equivalent one which does delay, which is tilde, and they're kind of opposites of each other. So bang of A says that, so under the normal demand rules, if you've got an argument over here that is never demanded by the body, we would say that this is not demanded. But with a bang pattern, we say it always is demanded. So effectively, we're saying evaluate it, like as soon as the function starts, if you like. But GHC can do it whenever, and it can propagate that analysis to callers as well. So what this says is we will demand that the argument be in weak head normal form for this function, whereas tilde is the opposite. It says that we even if it does get used in pattern match, I won't go into this one, but it's kind of the opposite of bang pattern. And why is that nicer? Why am I recommending? So what's the answer? We use bang here, and in particular we use bang here on the A. Why is that nicer than using strict application over here? It's because arguments are defined once but used many times. That's one reason that the A could be used several times over in the body here. And if we bang it here, we don't have to worry about the many places we might use it elsewhere. It also is easier to see for someone else coming along and reading your code. They can look not in the body, which is often large and complicated. Maybe A is used on the next page if you've got some big function. But if you can see in the definition, in the argument position that something has got a bang pattern on it, you can see immediately that it's demanded without having to look at the body. So stylistically, and because it's easier, it's harder to get wrong, our recommendation is usually to use bang patterns rather than using it in the expression syntax, use it in the pattern matching syntax. And if necessary, that means that you can introduce a let. So you say, let x prime bang equal blah, 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 blah in blah, 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 blah x prime. If you need to introduce strictness locally, it's still usually nicer to do it with a bang pattern like this rather than to put somewhere in, let, because the alternative is you have to do this, let, sec, blah, 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 blah. And so that style is usually nicer. And I think that's where I will stop. Thank you very much.
So I think we have time for questions.
All right.
So I have a question. How, like in CPX style, when you're building a long composition of functions instead of like an accumulator here, how much memory you're actually using because of building a pretty long expression of.
You mean if you're using like the style of one list producer consumer that you chain together? Do you mean? Yeah. Those things like this example earlier, right back at the beginning. Where was it? This one. This is like an example. That's the sort of style you mean?
Yeah, for example. But
so this will run in constant space.
Okay, so it's not exactly what I was meaning. Like when you have kind of like accumulator.
Yeah.
But you instead of like adding here, just composing functions. So this accumulator is just a long composition of functions that at the end will be evaluated against some argument.
Recursion in a
Yeah.
continuation bypassing style.
Yeah.
Yeah, so the important point there is whether you're doing it in a fold L style or a fold R style. If you're doing it in fold L style with an accumulator, you can't reduce the composition. So that will build up. That is definitely building up, a chain of not funks because they're not funks, but it is building up a delayed. Each of those things is a function, and doing the composition builds another function, and that will definitely build up a chain. But if you do it in the fold R style, I think actually you can get it to run in. The CPS stuff is quite subtle when it comes to, you have to think really quite hard about what's going on. But yeah, in the CPS style, it's much better to do things in the fold R style than the fold L style. The fold L style, you can't get away from building up the function dynamically and then applying it later. Whereas in the fold R style, you can actually do some compile time inlining and stuff. I don't know if that answers the question. But it's definitely building up a big expression if you're doing D-list style composition, if you do it in accumulator style.
So I have two questions. So what I usually tend to use, especially in a parallel setting, is force instead of seek, because it gives me guarantee on the whole structure. Do you have any thoughts on that?
So let's see. This is force is the DeepSeek one, isn't
Yes,
it? Yeah. Yeah. So I have there's a whole bunch of slides here which you can look at later on normal form and the DeepSeek library. Where was it?
You need an instance of NF data for the structure. So that's the first difference.
Yeah. So the DeepSeek library is all about normal form. And normal form, unlike weakhead normal form, where it's just the first constructor, normal form is evaluating all the way down. And so this is the one you were after, force. So it's different, right? Because the thing I was talking about with bang patterns and with seek and with strict apply is weakhead normal form evaluation. And what you're talking about is normal form evaluation, which uses this type class. So it builds up normal form evaluation by repeated weakhead normal form evaluation all the way down the structure. So actually, here's a very interesting question. Why does seek have to have the type that it does, whereas force can have the type that it has? So imagine instead I had this is wrong seek, and wrong seek has the type A to A, and I want to tell you, and this doesn't work, but why doesn't it work? Why could we not have a primitive like this that did evaluation, that added strictness in the way that the seek operator does? Why can't we do that? Why doesn't it make any sense? Why does it have to be seek that's A to B to B? So if I have to do things like seek X, returning f of X. I can't.
Because in the first case, A would already be evaluated to normal form because it would be demanded, right? And in the second case, it evaluates A when B is demanded. So
yes, you have to attach. This would make sense because you'd be saying when A is evaluated, evaluate A, but that's already what the identity function does, and that doesn't gain you anything. That doesn't change. Whereas seek is attaching to the evaluation of something else. It says when you evaluate this, evaluate that, and that gives you any control. When saying when you evaluate this, it doesn't add anything at all. So you have to, when this is evaluated, evaluate X first. Whereas saying F, when you evaluate X, evaluate, we haven't changed anything if we do it this style. But with force, with DeepSeek, why does it in fact make sense to have well, you can see the type on the screen there. It is, A to A, provided that it's in, A is in DeepSeek, or NF data rather, sorry. NF data A. Why does that make sense now?
Because it's going to normal, not weak.
That's right. You're attaching. So it's like you're attaching extra rules to evaluation. When in seek you're saying attach when that is evaluated, when that's evaluated to weak head normal form, evaluate this to weak head normal form. Force says when this is evaluated to weak head normal form, actually evaluate it to normal form. So that is different to, whereas it's a tautology or a useless to say when this is evaluated to weak head normal form, evaluate it to weak head normal form, useless. When this is evaluated to weak head normal form, evaluate it to normal form, useful. So yeah, so force does make sense here, and it indeed is probably the most useful, as you were saying, probably the most useful of the functions in the NF data class, or helpers that come from the NF data class. DeepSeek is there just to be similar to seek, and strict apply is similarly. And there is no corresponding bang pattern for DeepSeek, because it wouldn't really make much sense. But force is probably the next best thing.
And the second thing, which I discovered quite recently when exploring core, is that we don't actually have to be smart and rely on our reasoning on the strictness, because core has strictness annotations. I haven't found it documented apart from an obscure GHC doc somewhere in code. But it can basically say how strict the arguments are.
Yes.
For any function.
I don't have it on the slides on this one. Yes, indeed. So GHC does do strictness analysis. It's moderately sophisticated in its strictness analysis. Indeed, it can make the stupid version of sum into the good version of sum when strictness analysis is turned on, which it is with -0. Sorry, -0(1) or -0. And yeah, indeed, if you look at the sort of intermediate output of the compiler, it will tell you, and if you know how to read it, which, as you say, is in some obscure wiki page somewhere, it will tell you what the strictness of each of those arguments are, and that sometimes can be the best way to find out if it's something complicated.
So you said it's reasonably good. Can it be different in runtime than what?
No, strictness analysis is a compile time analysis, and then the compiler will transform the code based on the result of the strictness analysis.
Yeah, but can an argument be of a different strictness in runtime than during the strictness analysis?
No, because the strictness analysis is conservative. So the strictness analysis can believe it's non-strict. Let's be more precise. It errs on the side of caution, safety. The strictness analysis might say that it's non-strict, when in fact at runtime we can discover that it's strict. And so the normal evaluation will do the normal thing. But the strictness analysis can sometimes discover that things are strict. And when it does discover that, it's always right. But it's conservative in that way. Yeah. So sometimes you will know that something is strict because you can analyze it better than the compiler can in particularly complicated cases. Although actually in other cases it can figure it out and you can't. Because it's tireless and we get tired. Yeah, so the point is that you don't necessarily want to rely on strictness analysis for particularly subtle things. Like we would still define sum, with a strict accumulator, even though maybe strictness analysis will sometimes get it, because in particular it means that when you're running without optimizations, if you put the bang pattern in, this version will run in constant space whether you run with -0 or not, and that can be important. You don't want needless, massive space leaks in your non-optimized version just because, I sort of rambled. Does that answer the question?
Yes.
Okay. All right. All right? Yeah.
Could you go to the definition of sum tree, the one that was used in split dollar?
Yes. Where was it?
My question is, does GHC know it's tail recursive?
Oh, yeah. GHC knows it's tail recursive.
And how does it know? Does it inline? Because like from the syntactic point of view, it doesn't get tail recursive, only after I inline the
Where did I go? That was it. Sorry, there we are.
Yes.
Oh, yes, this is only tail recursive. You can only see this is tail recursive once you inline the strict apply. You're quite right. So once you inline $bang, it will turn into the seek version. Now, strictly speaking, the seek is in the tail position there, but actually the seek itself, basically turns into a case analysis, strict case analysis, which GHC core can do, and then you end up seeing that go is in the tail call position.
I see.
So yeah, it's not immediately syntactically obvious here.
So this relies on the fact that $6 is inline.
I suppose so, to say that it's, but actually, even if you ran this, even if GHC could not inline strict dollar, this would still run in constant stack space just because of the way that, just because of GHC's normal evaluation mechanism. It doesn't need to reserve stack space for making the, because in that case, it is $bang that is in the tail call position, and so it makes without reserving any stack space, it can go straight to calling the $bang function, and $bangs, if you look at that, will have the F in its tail call position, which in this case is go. So it still all works out either way, whether you inline it or not, actually. Yeah, it's interesting. So the difference is whether you can see that it's in the tail call position statically. And if you can't expand $bang, you can't see it statically, but the normal mechanisms will still cause it to use no stack space. But if you can inline that, then you can see syntactically at compile time that it's definitely tail recursive, which may enable further optimizations.